Hi, welcome to Software Architecture in Practice. This is all about Chapter 3, where we look at understanding quality attributes. This chapter kicks off with a quote that seems pretty fitting. This is by William Foster. He says, "Quality is never an accident. It is always the result of high intention, sincere effort, intelligent direction, and skillful execution." And as we dig through this, you're going to see that functionality is often the thing that we think about. What does the software do? And getting quality in how that function is delivered takes a lot of thought and consideration to make sure that performance is good, usability is good, it's modifiable and maintainable for the future. So lots of intention here. So let's dive in. There are many factors that determine the qualities that need to be met in a systems architecture, and these factors are not just functionality. Functionality, when we think about just functionality, we can be talking about the system's capabilities, what can it do, the system's services, what do we need to carry out those capabilities, behavior, what does it do as it's doing those responsibilities that we give it. And oftentimes when we're talking about functionality, we let it take the front seat of our development project. And that idea is very short-sighted. And the reason that's short-sighted is because you can make it do all of these different things and set it up, but if you're not thinking about things like performance and modifiability and other quality attributes, your system is going to have the potential that users won't want to use it. It will be too clunky and cumbersome and just is not something that people will want to use. So you have to consider more than just functionality when you're building a system. So before we get into the quality attributes, we need to understand a little bit more about what functionality is. When systems are redesigned, it's usually not because they're functionally deficient. If you need to give a system an overhaul, oftentimes the functionality is really pretty much identical. So why would you go about redesigning a system? And there's a couple of different common reasons. So let's go through the three most common. First one is that the system might have something about it that makes it difficult. Okay, it could be difficult to maintain. That means if you need to install a security patch or fix a bug, it's cumbersome and hard to do that. It could be difficult to port or move from environment to environment. It could be difficult to scale. As you get more users or more data, you might need to scale your system. And if those things are difficult to do, you might consider a redesign of your architecture. So that's one way you might, one reason you might redesign. And you can see from those different things, the functionality is going to be the same. It's really just the architecture behind it that you're talking about. Another common reason for redesign is that it's too slow. Okay, your performance isn't very good. Your users are having delays when they're trying to do an action. Different areas of slowness. It could even be in your development pipeline where it's too slow for you to get changes deployed and in front of your users. And then a third common reason that a system might be redesigned is because the system is compromised. And this means that a hacker or some nefarious entity has gained access to information that they should not have access to. It could be user information, it could be bank information, it could be activity, it could be any number of things. But if your system is compromised, you're going to need to redesign your system so that it can be more resilient and secure. So those are some of the reasons you might redesign a system, and that's why we need to be considering our quality attributes at the beginning so that we don't run into these things down the road. We want to try and prevent these. So that's why we're thinking about quality attributes as we are looking at our system architecture. Functionality doesn't determine your architecture. We talked about architecture in chapter 1 and the different structures and elements that it's built up from. And if we're given a set of required functionality, there's no end to the different architecture you could create to satisfy that functionality. You could divide that up in any number of ways. So instead, what we need to do is we need to design our system as a structured set of cooperating architectural elements, like modules, like layers, classes, services, databases, apps, threads. Any number of cooperating architectural elements can be used to design the system. So even though the functionality is independent from any particular architectural structure, it is achieved by assigning responsibilities to those architectural elements. And that results in one of the most basic architectural structures, the module decomposition. That's where we split up the system by different parts, usually based on functionality. And that even is just so that you can allow for your engineering team to be working and building in parallel, because they can work on those different modules, those different parts, without overlapping each other. So when we're thinking about this, we're looking at you, the architect. You're a happy architect. And what you care about is you do care about the functionality, but you care about what it's doing to other qualities. So there's a couple of different things that functionality can use, functionality does to other qualities. One is it's going to interact. Functionality, how does it interact with other qualities? And functionality, how does it constrain other qualities? So you, as the architect, your focus is on those two things. And you want to make sure that you're delivering this, but you have to also consider your qualities. So how does that functionality interact with and constrain other qualities in the system? So since we're looking at those functional requirements, we need to be able to define them. And that's not always an easy thing to define. If we look at quality attribute requirements, that's a little bit more straightforward. So for example, if you're talking about performance quality, that's going to has to do with the system's timing behavior. If you're looking at the modifiability, that has to do with the system's ability to support changes in its behavior or other qualities after its initial deployment. So how easy is it to change later on? If you're looking at availability, that has to do with the system's ability to survive failures. So quality attribute requirements, when you have a specific attribute you're looking at, a specific quality you're looking at, that's pretty straightforward to define. But when we get back to functional requirements, it's just not a straightforward thing to define. Functionality is the ability to provide functions. If you know anything about writing a definition, you generally can't use the same word in the definition as the word you're trying to define. So saying functionality is the ability to provide functions, that's very unclear. So to try to boil it down in the most simplest way that we can, when we're thinking about functionality, we're talking about what does the system do? Okay, what does it do? And when we're talking about quality, we want to know how well does it do it? What's the grade? Is it an A? Is it an F? How well does it do it? So what does the system do, and how well does the system do it? What are the things that we need to consider when we're looking at quality attributes? Well, first of all, we need to talk about how we discuss quality attributes. As an architect, you need to be able to talk through these ideas with other engineers and with other stakeholders. And there are three main problems that usually come up when you're trying to discuss quality attributes. The first one is that you have untestable definitions. What do I mean by that? If you say that a system is modifiable, how do you test that? Because every system is modifiable for maybe one set of changes, but not modifiable for another set of changes. So it's difficult to test. Or how do you test if something is brittle versus robust? A system could be robust in one area, brittle in another area. How do you test those things? Another problem when we're trying to discuss quality attributes is we have overlapping issues. So for example, if we're trying to talk about a denial of service attack, is that an aspect of availability, or an aspect of performance, or maybe security, or maybe usability? It could fall into any of those categories, so that can sometimes make it difficult to discuss because those different areas all take different considerations. Our third problem when we're discussing problems, having problems with discussing quality attributes, is differing vocabulary. So you'll find that there are engineers who may be more focused on things like performance, or maybe more focused on usability and modifiability. And so we have these different communities, and they all may have a different word to describe the same event. So for example, if you're in the performance community, you're more focused on performance. An occurrence could be called an event. If you're in the security community, it might be an attack. Availability community might call it a fault. Usability community might call it a user input. These can all describe the same occurrence, but they all use different terms. So those are some of the issues that we're going to run into when we're discussing them. And we need to have some solutions for how to deal with that as we get through this chapter so that we can all be on the same page as we're discussing these quality attributes. So one of the first solutions is quality attribute scenarios. And what that is going to help us solve are these first two problems. Okay, so quality attribute scenarios, that's a solution for untestable definitions and a solution for overlapping issues. So these scenarios that you'll be seeing, we'll go through what makes up a scenario, and each of the following chapters that go through quality attributes will give scenarios for each attribute. These scenarios are a way of characterizing the quality attributes. So they can include attributes that describe some property at the system runtime, usually. So availability, performance, usability, things that happen during runtime. We also have a solution for discussing quality attributes for our third problem. And if we go back here to our problems, we can illustrate concepts in a common form to help with the differing vocabulary. So by illustrating them in a common form, the common is the key word here, that's going to help us all be on the same page. So this method of illustrating these concepts, that's going to be useful for describing some property of the system during its development. So modifiability, testability, deployability, those are the types of things that we can illustrate. So those are the different solutions that we'll have as we discuss quality attributes. And that's pretty much what the rest of this chapter is about, is breaking these down a little bit more. All right, so quality attributes. These can never be achieved in isolation. So if you achieve one quality attribute, like performance, it's going to have an effect on other quality attributes. It could be positive or negative. Let's actually take the example of portability. The main technique for achieving portable software is to isolate the system dependencies, and this usually introduces some overhead into the system's execution because we've isolated these dependencies. Typically, this overhead is in the form of a process or procedure boundary, and then that is going to hurt performance. So we've improved portability, but it impacts performance, in this case, in a negative way. So that's important to understand, that you can't just work on a quality attribute in isolation. It's always going to impact others, and you need to understand those trade-offs. All right, so we talked about those solutions for these problems with discussing the quality attributes, and we're going to focus on the solution for these first two for a little bit here, which we said were scenarios. Okay, so this section is all about defining the parts of scenarios. Quality attribute scenarios, so that solves our untestable definitions and our overlapping issues. And these are usually these include the attributes that describe some property of the system at runtime, like availability, performance, usability, those types of things. So when we are talking about the scenarios, we have 6 different parts. The first part is the stimulus, and we're going to represent that stimulus with an arrow. So a stimulus is an event arriving at the system. Okay, this event could be a number of different things. So it could be, if you're part of the performance community, you might call it an event. If you're part of the usability community, you might call it a user operation. If you're part of the security community, you might call it an attack. Okay, so these types of things could be a stimulus, just depending on the context that you're discussing. It could also be that we're using the stimulus to describe a motivating action for development qualities. It could be, if you're talking about modifiability, it could be a request for modification. So that's some motivating action. Or it could be, if you're looking at testability, you're looking at the completion of a unit of development. So we'll just shorten that and call it unit of dev. So the completion of some unit of development could be your stimulus. So that could trigger some next step. All right, so there's our stimulus, and we are representing stimulus with an arrow. It's some event that's arriving at the system. All right, the stimulus source. Where does that arrow come from? Where does our event come from? We're going to have it come from this archer here. So where does it come from? Okay, this could be, let's see here. So the stimulus, we said, it's an event arriving at the system. The source, where does it come from? Some entity must have generated the stimulus. It could be maybe a human, so some sort of a user interaction. It could be a computer system that sent a stimulus. It could be any other actor. Maybe you have a system that has sensors that could be sending a stimulus, sending an event. So the source of the stimulus may affect how it's treated by the system. So if it comes from a human versus maybe like from a trusted user versus an untrusted user is going to go through a lot more scrutiny with whatever stimulus they sent versus a trusted user. So depending on where it comes from, it can behave differently. The next one is the next part for our scenarios is the response. So we already have the stimulus here, and we need to somehow respond to that stimulus. So when that stimulus arrives, it's whatever the response is, whatever activity occurs as a result of the arrival of that stimulus. Okay, so our response, we're going to just represent it with a target here. So the response is something the architect undertakes to satisfy either the responsibilities of the system for runtime qualities that should be performed in response to the stimulus, or it's the responsibility of the developers for those development time qualities that should perform in response to the stimulus. So depending on if it's a runtime event or outside motivation, that's going to differ with what the responsibilities are and what the response is. So for example, if we look at a performance scenario, when our stimulus, our event, arrives to the system should process the event and then generate some sort of response. So the performance is what response is generated when it arrives. All right, response measure, as you can imagine, when our stimulus arrives in the system and we get a response, we want to keep track of how long that takes, or maybe the quality of how it happens, some sort of measure for that response. We're going to represent that with this little stopwatch here. So how do we measure it? If we look at that performance scenario again, our event arrives, so our stimulus arrives, we get some sort of response, and the measurement might be the latency. Latency is the delay before a transfer of data begins, following the instruction for its transfer. And so it's a measure of time in that case for performance. So when the stimulus arrives, how much time does it take for that response to get back to the user or the system? All right, so we've got these first four. Remember I said there are 6 parts. These first 4, stimulus, stimulus source, response, and response measure, these are the heart of our quality attribute specifications. This is the main part here. But there are 2 more characteristics that we often overlook that are important to keep in mind. The first one of those 2 overlooked parts is the environment. So we have all of these things that are happening here. And what does the environment look like when these things are happening? Let's put a couple of different examples here of what our environment might look like. So first, maybe it's an overload condition. Okay, we'll make that overload be like a thunderstorm here. Okay, the environment is that it's overloaded. Maybe it's normal conditions. Everything's working great. Maybe it's some other relevant state. Here, this is fog. Okay, what does that environment look like for these activities that are taking place? These first 4 things that we talked about, what is the environment for these? Okay, it could also refer to the state where the system isn't running at all. So maybe when it's in development or in testing, or it's refreshing data, or it's recharging its battery between runs. The environment can be a lot of different things. For example, if we're looking at a deployment pipeline, so the process that a team goes through when they've made their code changes and they're ready to push it all the way to production, Generally, what a team is going to do is they're going to have a code freeze. So they'll say a specific date or a specific time where they say, okay, this branch is ready for our release, and we're not going to add anything more to it, and they're going to freeze that branch. And the reason they do that is so that the code can go through a number of tests, unit tests, integration tests. It can be deployed to a staging environment, or a QA environment, so that the quality assurance engineers can test it and make sure that everything is working as expected. So they freeze that branch so nothing else is introduced while all that testing is happening and while everything's prepared, and then the code gets deployed. So a request for a modification might arrive. So that request for modification, remember we said that motivations outside of the code could be the stimulus. So maybe there's a request for modification. Our stimulus arrives to the team. Okay. If it's before the code freeze, maybe it's that normal condition and we can go ahead and push those changes in. But if it's after the code freeze, before it's been deployed, it's maybe some other relevant environment, the fog here in this case, where that code is going to be, it cannot go in. That request is going to be treated differently before the freeze than it would be after the freeze. Another example might be if there is one failure for a component, that might be treated like an anomaly. It's not a big deal. It's probably a one-off. But if that same failure, or if a failure occurs multiple times in a row, so maybe 5 times in a row, that's going to be treated differently than a one-time occurrence. Successive failures, you're probably going to put a lot more attention on right away, whereas first failure, maybe there's a little bit less concern. Okay, so that's environment. And the last part for our quality attribute scenarios is artifacts. In this case, I've got a little, I don't know if these have kind of come back, Polaroid pictures, or an instant picture. So you take a picture and you've got the film. So basically the artifact is some capture of what was going on, something about, it's usually captured as just the system or the project itself, but sometimes it's more helpful if it's more precise. The artifact could be a collection of systems, it could be the whole system, it could be one or more pieces of the system. So what are the parts involved in what we're looking at? Those are the artifacts. Alright, so now we've gone through all 6 parts of the quality attribute scenarios. So we have the stimulus, which is some sort of event. We have the stimulus source, where does it come from? We have the response, what happens when the stimulus arrives. We have the response measure, which could be how much time does it take, or some other form of measurement. We have the environment, is it normal, is it overloaded, is it some other environment? And we have artifacts. All 6 of these things together make up those quality attribute scenarios. If we want to look at this in a visual form, we can talk about our source. This could be internal or external. This could be people, it could be hardware, it could be software, it could be physical infrastructure, physical environment. It doesn't have to be just something in the system. It could be outside of the actual software itself. Stimulus, this could be a fault, like an omission, a crash, incorrect timing, incorrect response. Those different things are different faults that could occur. The artifact in this example would be something like processes, communication channels, storage, affected artifacts in the system's environment. The environment in this example could be normal operation. It could be during startup, it could be during shutdown, it could be in repair mode, it could be degraded in operation, it could be overloaded in operation. All of that's the different environment that the stimulus and response are in when it's happening. Response, again, is what happens when the stimulus arrives. So in this example, if it's a fault, The response could be that we're preventing the fault from becoming a failure. It could be that we're just detecting the fault. It could be that we're recovering from the fault. So whatever the response is, that's the response. And then the measurement, how do we measure something like this in this example? It could be the time or the time interval when the system needs to be available again. It could be an availability percentage. It could be how much time does it take to detect the fault. So just depending on whatever your response is, that can influence what it is you're actually measuring. Let's do story time. So one of the authors, Rick Kazman, when he was doing an architectural analysis on a complex system that was created by Lawrence Livermore National Laboratory, as he was kind of researching what they do, the word security is mentioned a lot in what types of things they carry out all over their website. So they focus on nuclear security, national and domestic security, environmental energy security. So you assume that there's a lot going on with security. And when he talked to his clients about the quality attribute concerns for the system that he was analyzing, they never mentioned security. And so he questioned that, but they were really straightforward with their answer. And they said, we don't care about this, not my problem. We, being the software architects and the engineers, the developers, they said, our systems are not connected to any external network. So any of their information, it can't get out. There's like a wall around it. There's no network that will leak it out. So our systems are not connected to any external network, and we have barbed wire fences and guards with machine guns. So somebody for this company was interested in security, but in this case, it wasn't the software architects that were concerned about it. So software architecture, the software architect might not bear the responsibility for every single quality assurance requirement. So that's just something to keep in mind, and kind of an entertaining story that not always will the quality attributes that you're concerned about, not all of them are going to be your responsibility to sort out. So there's a little story for you. Okay, so we've talked about the different scenarios now, so we can talk and reason about quality attributes, having these scenarios. How do we achieve them? And there, hopefully you've already learned a bit about design patterns and tactics, but we'll go over these just a little bit with what is an architectural pattern versus a tactic, and how do those help us achieve quality attributes. So a tactic, let's just break it down into a very simple definition. A tactic is a design decision that influences the achievement of a quality attribute response. So this directly affects the system's response to a stimulus. So remember, if we're talking about our quality attribute scenario, it's impacting this part here. Okay, the tactic cares about the response to a stimulus. So really, more specifically, it's just the target. So you can think of a tactic as a design decision. Let's think of it as kind of like a play. Like if you're a coach for a sports team, what method are you going to use to handle it? An architectural pattern is going to describe a particular recurring design problem. So it's a pattern. It recurs. It's a common thing that engineers come up against that arises in specific design contexts, and then the architectural pattern then presents a well-proven architectural solution for that problem. So patterns are typically comprised of multiple design decisions, and that also means that it's often comprised of multiple quality attribute tactics. So if we're saying that our tactics are our design decisions, then maybe what we can say for our patterns is they are a collection of those tactics. So kind of like a playbook here. So we've got more than one tactic that makes up the architectural pattern. Okay, so as a result, we do frequently need to make trade-offs among quality attributes because different tactics are going to be useful for some attributes. But remember, they can, if you focus on one attribute, it could negatively or positively impact other attributes. So understanding what those trade-offs are going to be important for you to understand what quality attributes you need to pursue and prioritize. And that's something that you also need to define well with your stakeholders early on so that you know what your focus needs to be on. When we discuss these different patterns and tactics, we often discuss them as though they're foundational design decisions. And the reality is that the architecture often emerges and evolves as a result of many small decisions and business forces. But say, for example, you are starting to build your software system, and you've got a nice little architecture here. So here's our cute little cottage. It looks well balanced, well formed. So for example, if this is a software system, maybe it started out as tolerably modifiable. You can make changes to it pretty decently, but over time, that modifiability might deteriorate. And that could be through the actions of developers that are adding features or fixing bugs. Maybe they're just not focused on architectural integrity. Maybe there is a timeline that is being pushed onto them, and so they're not able to think through it as quickly as they want. And so what you eventually end up getting is you start to get kind of this hodgepodge structure that builds on the foundation that you started, but maybe it's got some crooked windows and some random bits and pieces that are kind of holding it together, and it's just being balanced with a little bit of scaffolding. So these types of things it's going to impact your quality. And so developers, we call this the death by 1,000 cuts. It's when all these little things start to add up and make it less of whatever quality you started with. So developers might have to make suboptimal decisions, basically not the best decisions, due to either a lack of understanding of the structure of the system, again, schedule pressures, lack of clarity in the architecture from the start. Maybe they just don't know what it was supposed to be, and so they're just building on it, but it's kind of building in a funny way. And this kind of deterioration is a form of technical debt. If you know of technical debt, it's the technical improvements that you want to make, but aren't necessarily going to change functionality, but it would be helpful in the future to make those changes. This type of debt we call architectural debt. Okay, this whole mess of a house up here, that's our architectural debt, where it's not a cohesive structure anymore. It's a hodgepodge. It's kind of just pushed together. And in order to reverse this debt, this hodgepodge of stuff, in code, what we need to do is we need to refactor. And that's where we leave the functionality as it is, but we change the structure of the code. And that's, remember, what we talked about pretty early on in this chapter, where a redesign of a system usually has identical functionality, but because of performance or other possible influences like this architecture debt, we have to change things. We have to refactor. When we talk about code refactoring, that's again to reverse our architectural debt. It could be because we're trying to improve our security. Remember, we talked about how one reason you might have to redesign your system is because it's been compromised. We might need to improve performance. Maybe it's too slow for your users. We need to have it perform better. And it could also be that your actual development process is going too slow and you need to improve the system's modifiability. And that, remember, is the ability of a system to accept changes. So security, you're placing different modules in different subsystems based on the different security properties. Performance, you're maybe removing some bottlenecks, you're rewriting the slow parts of the code. Modifiability, you're making it easier to change. So this code refactoring, this is a mainstay practice for agile development projects. Agile is a very common way of developing. You often see it compared to waterfall. Waterfall is where you make all of your planning up front and then work on all of the code, and then you deploy it all at the very end. Agile is you start with smaller deliverables and get it out the door, usually with faster turnaround and faster feedback. So anyways, code refactoring is very common in agile development projects because you're deploying some things, getting it out the door, and then starting to refactor as you see how it's behaving. And it's a cleanup step that makes sure that teams don't produce duplicative or overly complex code. You're keeping it dry. Don't repeat yourself. You are making sure it's not overly complicated. You're looking at YAGNI. You ain't gonna need it. You didn't add something that you don't need. That's what your code refactoring is giving you opportunities to do. But this concept, it doesn't apply just to Agile. It applies to architectural elements too. All right, so in summary, as we talked about this whole chapter, functional requirements describe what software does. Quality attribute requirements describe how well the system does what it's supposed to do. Quality attribute scenarios help capture and express the quality attribute requirements. And remember, that was 6 different parts. We have the source, which is hard to see on the blue background. You have the stimulus. You have the response. You have the environment. You have the artifact. You have the response measurement. How many do we have now? 1, 2, 3, 4, 5, 6. There's all 6 of them, so I know they don't show up quite as well, but so those 6 different parts are our quality attribute scenarios. And then we have the architectural tactics. Remember, that's like a sports play. The tactic is that design decision that affects the quality attribute response. It's your play. The focus of a tactic is on a single quality attribute response. It's not a bunch of them. And then architectural patterns describe a particular recurring design problem that comes up in specific design contexts and then presents a well-proven architectural solution for the problem. So in this case, we're describing it as a collection of different tactics, as kind of like a bundle of tactics. All right, so hopefully that helps give you a better understanding of the quality attributes. And the next chunk of chapters for this unit is going to go through specific quality attributes that are then kind of broken up into those quality attribute scenarios as a way to define and describe them. Thanks for joining me, and I'll see you in the next chapter.